Hi, welcome to the poster session of our paper LogPar Logistic PARAFAC2 Factorization for Temporal Binary Data with Missing Values. I'm Ke Jingyin from Hong Kong Baptist University. This is a joint work with our collaborators from Georgia Tech, Emory University, and UIUC. Many real-world data are binary and are often collected over time. Irregular tensor is a very useful tool to handle such data. Irregular tensor is a collection of matrices with varying sizes in one dimension, and it handles the temporal irregularity in the data. However, our observations usually contain inevitable one-class missing values. Consider the example in healthcare setting. Values of ones in the binary irregular tensor represents confirmed diagnosis codes assigned by doctors, but the value of zeros can have two possible meanings. Either the patient doesn't have the disease, which means negative, or the diagnosis was not even performed, which is a missing value. In this paper, we aim to complete the missing data in this binary irregular tensor and also discover the meaningful latent factors at the same time. We propose a model called Logistic PARAFAC2 LogPar to tackle these challenges. First, we define an observation model that is suitable for the binary input. We assume that there exists an underlying tensor M, which is real-valued and non-negative. Then it goes through a quantization process to generate the binary data. The quantization uses a sigmoid function tailored for non-negative input that outputs a probability score. Then the entrants of Y take values of 1 with this generated probability score. Finally, from this clean data, we get the observation by sampling a subset of its positive entries. We further assume that the underlying real-valued tensor M has low-rank property, so we use PARAFAC2 factorization to approximate it. To handle the one-class missing issue, we propose to extend an effective PU learning loss formula to our logistic PARAFAC2 factorization. This loss function was proposed for positive unlabeled binary classification problem, and we map it to our setting by replacing the sample-wise loss function in its empirical loss by the entry-wise loss function that we derived for our logistic PARAFAC2 factorization. Finally, it leads us to the objective function as shown in the screen. Besides, we also incorporate two regularization terms. The uniqueness regularization term promotes factor invariance, which is known to improve the uniqueness of the solutions. The time-aware temporal smoothing helps discover smoother temporal vectors, and it takes the real-time gaps into account. We evaluate our model using 3 large-scale electronic health records datasets and compare against 4 state-of-the-art baselines, including 2 PARAFAC2 factorization models and 2 binary matrix completion and factorization models. We first split the positive entries in the raw data into training set, validation set, and test set. To perform the evaluation, we also randomly match 10 negative entries with 0 values for the positive entry in the test set. We use PRAUC as an evaluation metric due to the binary and imbalanced nature. We first measure the completion performance with varying ranks. The blue line is the results obtained by LogPar. As shown in the figures, it consistently outperforms all baselines for all target ranks in all datasets by a large margin. Then we fix the rank of all models to 30 and vary the missing ratio from 20% to 40%. As shown in the figures, LogPar still consistently outperforms all baselines for all levels of missingness, and is more robust to heavy missing. We also perform downstream prediction tasks, the heart failure onset prediction for Sutter and mortality prediction for MIMIC3. We fix the missing ratio to 30% and use a subset of the patients to train the model. Then we fix the learned factors and project the remaining patients to get their temporal factors. As shown in the figures, the latent factors discovered by LogPar outperforms the COPA and Spartan in both tests. To conclude, we proposed LogPar for binary irregular tensor factorization with missing values. LogPar is the first PARAFAC2 model considering the missingness, and we incorporated the PU learning, which greatly helps the completion. We proposed the uniqueness and the temporal smoothing regularization for better interpretability, and the empirical evaluation validates its effectiveness. Thank you for listening.